We'll be solving another transport problem. In this problem it states, a rigid vessel having a volume of 3 meters cubed initially contains a mixture at 21 degrees Celsius, 1 bar, consisting of 79% nitrogen gas and 21% oxygen gas on a molar basis. Helium is allowed to flow into the vessel until the pressure is 2 bar. If the final pressure if the final temperature of the mixture within the vessel is 27 degrees Celsius, determine the mass in kilograms of each component present. So for this problem, it might be a little easier to see what's going on by drawing a picture. So we'll define this as state 1. So state 1 is simply, just a box or some rigid vessel, which means the volume does not change. And it contains some nitrogen gas, N2, and some oxygen gas. And it has some initial temperatures. So we'll say that this temperature, T1, is 21 degrees Celsius or 294 Kelvin. And again, this is useful because the equations or the ideal gas laws are dependent on absolute temperatures or temperatures that deal with Kelvin. Okay, and then we have initial pressure, which is 1 bar, and we're given that the volume, which is constant, is 3 meters cubed. And then at the final state, we have a new component in this rigid vessel. So now we have nitrogen gas, oxygen gas, and now we have helium. So the final temperature, or T2, is going to be 27 degrees Celsius, or in other words, 300 Kelvin. And the pressure at 2 is going to be 2 bar. And again, the volume is constant, so this is 3 meters cubed. Okay, so the best way to go about this problem is using the ideal gas law. And our goal is to find the mass of each component. So since basically the ideal gas law is defined for state 1, we can use that to find how many moles of the mixture is at state 1. And we can use the molar percentages of the components of this mixture to find the moles of each component, which can easily be converted into mass. So let's start off with the ideal gas law at state 1. So we're going to say P1 V1 equals the number of moles of the mixture times R, which is the universal gas constant, times T1. And V1 is constant, it's 3 meters cubed. So I'm going to call this N1, which is the mixture at state. So that's nitrogen and oxygen. So we could rearrange this to find the moles of the mixture by writing this. P1 V1 over R bar T1. And we're given all these values at state 1, so we could find the number of moles of the mixture at 1. So this is going to be 100 kilopascals, so that's 1 bar. This is 3 meters cubed. R bar is 8.314 kilojoules per kilomole Kelvin, and this is 294 Kelvin. And the number of moles of the mixture at state 1 is simply 0.123 kilomoles. So technically from this, you could determine the mass of N2 and O2 with using the molar percentages, but we'll save that for later. We'll do all those mass calculations at the end. Okay, the next thing, our goal is to find how much helium in terms of moles there are at state 2. Okay, so what we're going to use is the ideal gas law, but what's special about this problem is that the volume is constant because it's a rigid vessel. So when you ever see the word rigid or it can't deform or something like that, that typically means the volume is constant. Therefore, so let me write out the ideal gas laws. Okay, so these are the two ideal gas laws at the two different states, and what we notice is that the volume of the two states are the same. Therefore, we can set the volume of both of the equations equal to each other. And just to let you know that N1 is the number of moles of the entire mixture, and N2 is the number of moles of the mixture at state 2, which includes helium. So we're going to set this equal to each other. So we could say that N1 T1 over P1 equals N2 T2 over P2. And then we could define the number of moles of the second state by just doing a little bit of algebra. So we could say that N2 is N1, and it's proportional by these values. So it'll be T1 over T2 times P2 over P1. And we have these values, so we can plug in everything in this equation to get the number of moles at state 2. So what we get is 0.241 millimoles of the mixture at 2. Okay, now you may be asking, why is this necessary? How are we going to use this to calculate helium, or the mass of helium, or the number of moles of helium? So basically what we have to do is understand that mass is conserved. Therefore, if we found the number of moles of the mixture at state 1, and we found the number of moles of the entire mixture at state 2, what we can say is that if we take N2 minus N1, that'll give us the number of moles of helium, since that's the only thing being added to from state 1 to state 2. So doing that subtraction, what you get is 0.118 kilimoles of helium. Okay, so the next thing we're going to do is calculate the number of moles of the constituents at state 1, so nitrogen gas and oxygen gas. So we solved for the number of moles of the mixture at state 1. Therefore, if you want the number of moles of N2, what we do is apply the molar percentage to that number of moles. So we could say that the molar percentage times the number of moles of the mixture will give us the number of moles of N2. So then this is going to be 0.79, which means that at state 1, 79% of the mixture is nitrogen gas in terms of moles. And we can do the same thing for oxygen. So this will be NO2, which is YO2, N1. This will be 0.21 times 0.123 kilomole. And these are the values you get when you calculate the number of moles of each component. But we don't stop there. Our goal is to find the mass of each component. All you have to do is basically multiply the molar mass of each component to its number of moles. So to find the mass of helium, all we have to do is take NHE, or the number of moles of helium, times the molar mass of helium. And that'll provide 0.472 kilograms of helium. And then we repeat the process for nitrogen and oxygen. So these are the values you get when you plug in these numbers into your calculator. So our goal was to find the mass of each component, and here are the masses. Again, this problem is pretty straightforward like the previous one, but the only difficult part is understanding the conservation of mass and how you can use the ideal gas laws at different states to find that change in mass, so to speak. Beyond that, the only other difficult thing about this problem is probably understanding what units to use and how to use dimensional analysis to get what you're looking for. So be careful of the units and be careful what you plug into your calculator. With that being said, I'll see you in the next video.